In section 1.5, we're going to look at solution sets of different linear systems, specifically homogeneous and non-homogeneous systems. So let's define what a homogeneous system is. This is going to be a linear system of the form AX equals 0. A is going to be an m by n matrix, and 0 is what we call the zero vector in Rm. 0 is just going to be a vector of all zeros. So basically this is any linear system where the right-hand side of the equal sign is all zeros. Or put differently, there are no constant terms in any of those equations. Everything is attached to some variable. So in this first example, we have x1 plus 10x2 equals 0 and 2x1 plus 20x2 equals 0. Let's look at the corresponding matrix equation. The first matrix is the coefficient matrix. That's what's attached to the x1s and the x2s. Remember that the first column represents the x1s, the second column represents the coefficients on the x2s. Then we're going to multiply by the vector x, x1, x2, and then it's going to equal the 0 vector on the right-hand side, 0, 0. So first let's note that the vector x, which is equal to 0, 0, that's the 0 vector, is always a solution to a homogeneous system, but does so trivially. So we call x equals 0 the trivial solution. So what I mean by that is if we take this matrix equation and we do this matrix vector multiplication we talked about last time, we can write this as the vector x, or the variable x1 times the vector 1, 2, plus x2 times the vector 10, 20 equals 0, 0. And we see that if we plug in x1 equal to 0 and x2 equal to 0, everything becomes 0 and we get the 0 vector. This is what a trivial solution is meant by. We can think about it as it's not interesting, it just happens with no real work being done. If you multiply everything by 0, you get 0. So in everything we talk about today, and everything we're going to talk about for the rest of the course with a homogeneous system, you always have a solution. It is always consistent, but the question is, are there any non-trivial solutions to the homogeneous system? That is, non-zero vectors that satisfy the system. So to determine if there are non-trivial solutions, we will consider the augmented matrix and row reduce, as we've been doing with a lot of problems so far. So if we take this first matrix, the augmented matrix, and we say negative 2 row 1 plus row 2 into row 2, the second row becomes all 0. Notice that when you're dealing with the right-hand side and you do row operations, if it's all zeros, they're going to stay all zeros no matter what you do. So we get a row of zeros, and we can see that we have a free variable here. We look at the row reduced matrix. This is a pivot, that 1. And this column right here is a free variable. It represents a free variable. That is, x2 is free. Which means that there are infinitely many solutions. We talked about last time that this is a consistent system with a free variable, and therefore has infinitely many solutions. x2 being free means we have infinitely many solutions. Let's think about what those solutions are. If we bring it back to an equation, we have 1x1 plus 10x2 is equal to 0. We get nothing from the second row, just 0 equals 0. That is, we can write this as x1 equals negative 10x2. So if we write, and x2 is equal to x2, that is our free variable. So we could write this as our answer, our solution is the vector x. That's going to be x1, x2. Written in vector form, this could be negative 10x2, that's equal to x1. x2 is equal to x2. And then we can take out an x2 from that vector, and we're left with negative 10, 1. So why this represents infinitely many solutions? Because any different value of x2 gives a different solution. And note that x2 equal to 0 gives the trivial solution. So that trivial solution is part of our answer that we wrote down here. So we say that a homogeneous equation, ax equals 0, has non-trivial solutions if and only if the system of linear equations has infinitely many solutions. But that is the same thing as saying that the system of linear equation has free variables. So in a homogeneous equation where the right-hand side equals 0, we know there are going to be non-trivial solutions if and only if there are free variables in our system. So let's look at another example. We're going to determine if the following homogeneous system has non-trivial solutions and then describe the solution set. So we just said that we're going to be looking for free variables to determine if this has a non-trivial solution. So in this system, we have two equations, three unknowns. We can write this augmented matrix 2, 4, negative 6, bar 0. And the second equation, 4, 8, negative 10, bar 0. And we can see that there's going to be at least one free variable before we even put this into echelon form. And that's because we have two rows, which means we have at most two pivots. There can only be one pivot in each row, so maybe our pivots are going to be here and here. In fact, that's where they're going to be. But you can't get a pivot in that second column or in all the columns. So therefore, you don't have a pivot in every row, which means that you're going to have at least one free variable. Then we know from the previous slide that if we have a free variable, that means that non-trivial solutions exist. So why is that the case? Because there is a free variable. So now we've determined that there are non-trivial solutions. If we would have found that there are no non-trivial solutions, then we're done. We can just say the solution set is 0 and we're done. But now we can actually find what those are and describe the solution set. So we have our matrix, our augmented matrix written here, and we're going to row reduce down to echelon form and then reduced echelon form. So let's go through these row operations. We have the first one is 1/2 row 1 is going to replace row 1. We want a 1 in that top left corner, so we're going to divide by 2 everywhere. The next one we want to get rid of that 0 underneath, so we can write -4 row 1 plus row 2 is going to be our new row 2. We get a 0 underneath, a 0 in the second column as well. And then finally we want a 1 in that bottom right corner. We'll again do 1/2 times the row. And this is echelon form. Row echelon form. In order to solve the system, we do want to put it into reduced echelon form, but it's nice to stop at echelon form to validate what we said before. We said that there's going to be 2 pivots in here, or at most 2 pivots. There they are. And we have our free variable, x2. That being said, let's put it into row reduced echelon form. The zeros aren't going to change no matter what row operation you do, so we can actually write those in right now. And the row operation we want to do is get rid of that negative 3 there. So we can do 3 row 2 plus row 1 is our new row 1. The second row is not going to change. We're going to get a 0 because 3 times 1 minus 3 is 0. And actually, the top row is not going to change past that because there's zeros in the second row. So this is row reduced echelon form, and that's what we want to put it in to solve this system. So now writing our variables, writing our equations out and think about our free variables. The first row gives us our equation. x1 is going to be equal to negative 2x2. This first row gives us the equation x1 plus 2x2 is equal to 0. And we're just going to write that as x1 equals negative x2. x2 is our free variable, so we're going to write that x2 is equal to x2. It could be any value. That's why we call it free. It's free to be any value. And then the third one is going to be x3 is equal to 0. That's from our second row there. So now we have our solution is given by those three equations. We can put it in vector form. The vector x is x1, x2, x3. We said that x2 is equal to x2, and now we have that x1 is negative 2x2 and x3 is equal to 0. We can take an x2 out of all of those, including the 0, which is 0 times x2. And we can write this as negative 2, 1, 0 times x2. I'll write that as x2 times a vector v. And that is our solution to this homogeneous system. It is infinitely many solutions. Given different values of x2, we get different vectors v. Now let's take a look at what this means graphically. So we have our vector v is going to be given by this vector right here. This is going 2 units in the x1 direction, in the negative direction, 1 in the x3 direction. Sorry, x2 direction, and 0 in the x3 direction. So this is our vector v. Let me draw it again. And the solution set, which was x2 times v, is just another way of saying that it's going to be the span of v, all linear combinations of v. And that's going to be a line through 0 in R3. So for instance, this point right here might correspond to negative 2v if I plugged in negative 2 for x2. And we could get anything along that line, right? Maybe this guy is 3v, and on and on and on. So now we're going to look at the same problem, but we're going to change the right-hand side of this equation. So this is a non-homogeneous system. That means that we don't have equal to 0 on the right-hand side of that equation. And let's see what happens with the same system on the left and just not zeros on the right. We have the same augmented matrix except for a 4 in that bottom right corner. And the row reductions are going to be the exact same except we're going to get different values on the right-hand side. In this case, we get a 6 and a 2. You can double check that yourself using the same row operations we did in the previous example. So this gives us the equations. First row gives us the equation x1 plus 2x2 is equal to 6. Since x2 is our free variable, we could write this as x1 is equal to 6 minus 2x2. And then our second row here gives us x3 is equal to 2. So writing that in vector form, we have x1 is equal to 6 minus 2x2. x2 is just equal to x2. That's our free variable, just like last time. and x3 is going to be equal to 2. And then we could split up that vector. We'll do this one more step. This is the same as 6, 0, 2 plus negative 2x2, x2, 0, x2. So to see that again, x1 is 6 minus 2x2, x2 is 0 plus x2, and x3 is 2 plus 0, x2. Kind of writing those zeros in there. We can break that up as two vectors, and we can pull an x2 out of the second vector, and we get this solution. And we can see that this is the same solution as we had. So here was our solution to the homogeneous equation. And we're just adding a vector to that solution. And we're going to call that special vector 602 p. So this is p plus x2v. So now let's look at what this means graphically. Our two systems had the same coefficient matrix, different right-hand side, and they gave us a slightly different solution, one with an added vector p. So what these are going to be are parallel solution sets of ax equals 0 and ax equals b. Let's draw what we have here. Let's say this is our vector v, right, goes through the origin, right, and span of v is our solution set for ax equals 0, just like we did in the example before this for a homogeneous system. How we get something for the non-homogeneous system is we take that vector v and we're going to add a vector p to that vector, and that gives us our solution p plus v. Also note that we could have done that from the origin, right? Because vectors don't have a position. We can start them anywhere we want. So this is just the vector p. And then, of course, we could get different things. So maybe this is the vector negative 2v. And if we add the vector p to that, we get another point on that line. And that point would correspond to, in this case, negative 2v plus p. The negative 2 would correspond to the x2 value. Here, the x2 value would be 1. Here we have 0v plus p. But whatever we have for that non-homogeneous solution is a line that is parallel to the line that we got for our homogeneous system. We have parallel solution sets for the homogeneous and the corresponding non-homogeneous systems. Another way to think about this is to think about lines in two space. We have y equal to mx. Let's just say we have that line. This is parallel to y equal to mx plus b for any b, for any real number there. That is, those lines have the same slope, and they are differing only by a different y-intercept. They are parallel lines. This is the same idea as the vector x is equal to x2v. Our solution is x2v, and it's parallel to x2v plus p. That p acting like the y-intercept when we're talking about lines. So non-homogeneous solutions and homogeneous solution sets, if they have the same coefficient matrix, are parallel solutions. So a recap of everything we just said there. When we had the homogeneous solution, that is equals 0 on the right-hand side, we got a solution set of x2v. And that was the parametric equation of a line passing through 0 and v. Parametric equation, the parameter there was x2. Different values of x2 gave you different points on that line. And it was a line that was passing through both 0 and v, 0 representing that trivial solution that we always have for homogeneous systems. For the non-homogeneous case, ax equals b, in this case b was non-zero, we got the same thing as we had before plus another vector p. And this is the parametric equation. Again, the parameter is the same. The parameter is x2. That's the thing that can change. It's like a variable of a line passing through p and v. No longer just the trivial solution that we have, but we have this p. The p is going to stand for a particular solution to the equation, to the system. It passes through p and v, and that's parallel to the other system. So again, let's think about the graphical representation here. And let's think about this theorem down here. So let's do the theorem first, and we'll come back to this graph. Suppose the equation ax equals b is consistent for some given b, and let p be a solution, a particular solution, hence why it's called p. Then the solution set of ax equals b is the set of all vectors of the form w equals p plus vh, where vh is any solution of the homogeneous equation. So in this picture we have this dot maybe is representing a particular solution, vh, of the homogeneous equation. And if I take that vector and I add a vector p to it, then we get a new solution, vh plus p. These are all vectors that we're talking about. And again, if I'm given a different solution, maybe this is vh, vh1 maybe, then if we add p to it, I get another equation, or another solution on that non-homogeneous solution set. Remember that the vectors vh are vectors coming from the origin, or we could think about them as coming from the origin. So maybe this is 0, 0, 0. We can get a different vector there if we had that as well. So another example here, let's describe the solution set of this linear system. It only has one equation. And we're going to compare it to another thing that's very close. Again, this is homogeneous, the first one, because we have equals 0 for every equation. We only have one equation. And this is non-homogeneous over here. We're going to compare what's going on in these two examples. So first, let's look at the augmented matrix. We're going to determine if there is a solution to the homogeneous equation and then what it looks like. So the augmented matrix is 2, -4, -4, bar, 0. And we can see right away that there is going to be a solution because there's going to be a free variable. In fact, there's going to be two free variables. First, let's put this in row-reduced echelon form. We can do that quickly by just saying 1/2 row 1 into row 1. And that'll give us 1, -2, -2, 0. We have a pivot in that first position, and then we have two free variables here. So, because there's free variables, that means that there's going to be non-trivial solutions. And we're going to try to find those non-trivial solutions. If we didn't have free variables, we'd only have 0 as the only solution. So let's look at the vector form of the solution. We have x1 minus 2x2 minus 2x3 is equal to 0. If we write everything on the other side there, we have x1 is equal to 2x2 plus 2x3. And there we get our vector for our solution. We have 2x2 plus 2x3 is x1. x2 is free. We can write that as x2 plus 0x3. And we have x3 is free. We can write that as 0x2 plus x3. That gives us two vectors here. We have x2 and x3. x2 is times the vector 2, 1, 0. The 2 and the 1, the 0 come from the 2, 1, and 0 in front of the x2s. And the 2, 0, 1 comes from the 2, 0, and 1 in front of the x3s. So in this case, we have x2 and x3 are our free variables. Another way to think about that is these are going to be our parameters of our parametric equation. Now let's look at the corresponding non-homogeneous solution where we have equal to 6 on the other side. Let's row reduce in the exact same way. We'll get 1, negative 2, negative 2, 3. 6 divided by 2 is 3. And we have very similar kind of solution. Again, we have x1 minus 2x2 minus 2x3 is equal to 3. So if you solve for x1, we get 2x2 plus 2x3 plus 3. x2 is free. We can write that as 1x2 plus 0x3 plus 0. And x3 can be written as 0x2 plus 1x3 plus 0. So what we're saying there is, let's multiply by the x2 is 210. So we can write x2 plus 210. What's multiplied by x3 is 201, just like the last example. And then we also have a particular solution, in this case 300, that represents the constants here, 300. So just like the previous example, what's different between the homogeneous system and the non-homogeneous system here is plus one vector p added on to the solution of the homogeneous system. And let's take a look at what that means graphically. So in this case, let's say that we have our two vectors. Right, let's write this down again. We have our solution here was x2 times some vector v plus x3 times some vector, we'll call it u, plus some vector p. Let's go back to the previous page and we'll say that again. So this is like saying this is equal to x2 times some vector v. V is the vector 210. Plus x3 times the vector, we'll call it u, and then plus some vector p. So here we have maybe, here is v and here is u. And those two vectors span a plane in R3 going through the origin. This is the 0 vector right there. So we could get to any point on that plane by doing a linear combination. So this would be 2v. And this vector right here would be 2v plus 2u, because I could attach two copies of u and get the diagonal of some parallelogram. I could take any linear combination of those two vectors and I can span that plane. But then if I want to look at the parallel solution, I can take any point on that plane and I can get to the corresponding point on the other plane. So let's erase everything I have here. So here we have the vector P, our particular solution. In this case, the vector P was the vector 3, 0, 0. So that's 3 in the x1 direction, 0 in the x2 and x3 direction. So if I take any point on the first plane through the homogeneous system, if I add a vector P to it, then I get something in the homogeneous system. Remember that this was 2v plus 2u. So then our new solution here would be 2v plus 2u plus p. And if you take any point in this plane, you can get to a point in the other plane by just adding the vector p. Those are parallel planes in R3, and those correspond to the homogeneous solution set and the non-homogeneous solution set.